Hello everyone, my name is Lucy Smith and I am a principal researcher in the Circular Economy Group at the Materials Processing Institute in Middlesbrough. Thank you very much for having me here today. Today I'm going to present the Circular Electric Steelmaking for 2050 project, a collaboration between myself and my colleagues at the Institute, Colin Atkinson, Adam Hunt and Andrew Buchanan. My colleagues at the Institute provide consultancy and research services to help improve processing, new product development, and reduce costs through applications of new technologies. This talk will cover the concepts of a circular economy and industrial symbiosis, and then a bit more specifically how electric steel making currently applies these theories through scrap utilization and the sharing of resources, and also how this could be improved moving towards 2050. I'll also then present the Institute's Circular Economy and Industrial Symbiosis Roadmap. This aims to support the electric steelmaking industry and others towards the circular economy. As you can see here in figure 1, this is a linear economy. It's the traditional take, make, dispose business model, where raw materials are extracted from the Earth's reserves, transformed into a useful product, put into service, and then retired as a waste, usually to landfill and certainly not recycled. Through the Sustainable Development Goals, the UN reported that global consumption of materials increased from 87 billion tonnes in 2015 to 92.1 billion tonnes in 2017. That was in line with economic development. So I'm sure that you can all agree that, as we know, we have finite resources in the earth, and so this increase can't continue in material extraction. As such, this brings us to the concept of a circular economy, a schematic of which is shown here in figure 2. The aim of a circular economy is to prevent the production of waste, thereby ensuring that all materials are recycled back into the supply chain. This can be achieved by making products more efficiently, increasing the in-use lifetime of the product, designing products to be reused as many times as possible, and designing them to be easily repaired. While residual materials or byproducts may still be produced in a circular economy, these resources are utilised to produce another product. And yes, the ideal situation would be that we would eradicate the requirement for raw material extraction and use in a circular economy altogether. But for now, where non-renewable resources are required, they should be acquired in a manner that's sustainable with no damage to the environment. The implementation of circular economy principles has found to lead to economic growth, reduced environmental impacts, job creation, and added value along the supply chain. Industrial symbiosis is an underlying construct of a circular economy, and a bit of a schematic here is shown in figure 3. Industrial symbiosis is a system within which the byproducts, previously known as wastes, of one industry become the raw materials, also known as the resources, of another. This creates an interconnected network of energy and material cycles with zero waste production. And these structures ensure increased material sustainability, reduced greenhouse gas emissions, and contribute directly to a circular economy framework. So to begin with, we'll talk about scrap utilization. When we consider a circular economy principles within the iron and steel industry, because we know that steel is 100% recyclable, both either in the electric arc furnace process for secondary steel making or as an additional source of iron in the primary steel making route through the basic oxygen furnace. And therefore, steel lends itself well to a circular economy. As shown here, it's been estimated that steel demand will reach approximately 2.8 billion tonnes by 2050. And due to the availability of end-of-life steel stocks, secondary steel production will only be enough to provide a third of the world's steel. This leads us to the fact that it's anticipated that the world will continue to rely on primary steel production until around the year 2100. Because a proportion of the UK steel scrap is exported annually, this leads to an increase in transport emissions, the potential for increased emissions due to poorer environmental management in other countries, and also a reduction in the security of supply of scrap in the UK. Residual elements in steel scrap reduces its value and inhibits its recycling into new steels due to metallurgical quality requirements in the melt. This can be overcome through design for disassembly, improved separation techniques, and incentives to reduce contamination. When the residual elements can't be reduced, the scrap is currently downcycled. But this scrap management methodology will not always be feasible, as the market for low-grade steel diminishes and primary steel production reduces. By moving up the waste hierarchy, away from recycling and towards reuse and manufacturing, the steel industry can become more circular. Manufacturers can take back components at end of life to be reconditioned to as a like or as new state for reuse, thereby increasing the life cycle of the product and reducing the environmental impact associated with recycling. So now I'm going to move on from scrap specifically to discuss the sharing of resources. Starting with slags. Electric arc furnace slags are crystalline, dense, and have a high skid resistance and tend to be utilised as concrete or road aggregates. Comparatively, stainless steel electric arc furnace slags are less dense and are used for cement and concrete. Although these routes to market are well established, research is underway at the Institute in partnership with other key players in the foundation industries to develop new processes and materials. The aim of this research is to increase the value of the steelmaking byproducts and to consider ways in which the environmental impacts related to those products and other products in the supply chain could be reduced. Zinc-rich dusts is valuable because of the high proportion of zinc which can be recovered from it. Existing opportunities for zinc recovery include a Welts kiln, and it's able to recover around 90% of the zinc from the electric arc furnace arising dust. Other thermal treatment options include rotary hearth furnaces, sinter plants, and even electric arc furnaces themselves. Alternative, less advanced methodologies include hydrometallurgical techniques such as acid, alkali, or ammonia leaching. Oxidative ionothermal synthesis, which has been found to be a potential technique for direct oxidation of metallic zinc from zinc oxide. And due to its low melting point and very low volatility, oxidative ionothermal synthesis has been identified as an environmentally friendly substitute for industrial organic solvents. Heat recovery is another byproduct of the steelmaking industry that can be looked at from an industrial symbiosis point of view. The heat that's recovered from electric steelmaking is characterized as low to medium grade heat, and therefore it is difficult to convert it into other usable forms of energy. The organic ranking cycle is a viable option for electric steelmaking. This involves the generation of steam that is then stored prior to being converted to electric power through an organic ranking cycle turbine, and then to thermal power, which produces heat. That can be used for recirculation, preheating, steam generation, and even in some cases, district heating. Over the last few slides, we've provided a bit of an overview of how circular economy and industrial symbiosis techniques are currently used within steelmaking. This slide shows the Material Processing Institute's Circular Economy and Industrial Symbiosis Roadmap. The Institute has recently been awarded £22 million by the Department for Business, Energy and Industrial Strategy, also known as BEIS, to support the UK steel and metal sectors across the circular economy, digitalisation, decarbonisation and advanced materials sectors. This has enabled the Institute to develop a circular economy technology centre that will soon be set up in our campus in Middlesbrough. The Circular Economy Technology Centre will tackle a range of circular economy and industrial symbiosis challenges. Some of those that we will begin with are shown here in our roadmap. And this will look specifically into the valorization of slags and other rich zinc byproducts and the increased utilization of scrap. This research will be funded using different funding mechanisms, and the processes that will be installed, specifically pyrolysis, pyrometallurgy, hydrometallurgy, separation and disassembly techniques, will also facilitate the research. So in conclusion, a circular economy has been found to support economic growth, reduce environmental impacts and create jobs and add value across supply chains. Currently, industrial symbiosis techniques are utilised in electric steelmaking for slags, but additional research is required into the optimisation of zinc-rich materials and the reuse of waste heat. At the Material Processing Institute, we are researching these methodologies and also aiming to use industrial symbiosis to increase the value and reduce the environmental impacts of these materials. This research will be supported by the Institute's new Circular Economy Technology Centre, which will enable our circular economy and industrial symbiosis roadmap to be realised. Overall, to achieve a sustainable circular economy, UK electric steelmaking must continue to increase its utilisation of high-quality scrap and reduce the volume leaving the country. Furthermore, the sharing of byproducts and other resources across the foundation industries and wider supply chains will reduce the environmental impact relating to landfilling and virgin raw material extraction, whilst having a positive economic impact. The research underway at the Materials Processing Institute is supporting the electric steelmaking industry and the wider supply chains to develop robust solutions to these global challenges. This slide contains the references that I have used in this work. And I would like to thank my colleagues again, Colin Atkinson, Adam Hunt and Andrew Buchanan for their contribution to this work. Thank you very much.